So the first presentation today will be a presentation from Professor Marc Sevaux on web services. So I will let him start. Yes.
Okay. Thank you. So let's start. I'm not very used to this microphone. Usually have a big voice. In French we say grande gueule, but okay. I need to do that for the people from distance. Hello, guys. Don't look at the number of slides. I'm going to skip a lot of them. It's just to let you some references and more about the work we are going to present here. When we submitted the title, we partially misunderstood the goal of the presentation. So introduction to web services is maybe a big word. People who will attend the lab session with Pierre Baumel will learn much more than what I'm going to present today. What I'm going to do today is give you some hints on the reason why we need some interfaces and why we need to be ready to collaborate with people who are keen on creating these web interfaces or interfaces in general. And I'm going to show you why we need them and through a list of projects we have in the past. I'm going to go very fast into some part of the presentation because it has been already presented by others. It will be reminded by some other people tomorrow or this afternoon or just after me. And I will focus more on the problem we have managed up to now. I will show you just some information about some records. So everybody knows the traveler's Salesman problem, which is the, let's say, root of the VRP problem. And just to remember you that it comes from a very long time ago by Sir Hamilton. So this is the Ecosian game. And in that game you have to create a route between the different positions, the shortest possible route, which is basically the shortest Hamiltonian circuit, the TSP. And it was followed by some of the papers. This is part of our history and scientific history. You should have a look to these papers. They are very interesting. You see that, for example, they use this distance matrix, and this is written like this in the paper. So they use this matrix, and if you look, it's in the resolution of this problem, it looks more like a paper drawing and resolution by hand than computer science. A bit later, you have this very famous game by Procter & Gamble, which put a price of $10,000 at the time, and to solve only 33 cities that every solver today can solve to optimality in a snap. And I give you here some other references about the different records. And the most impressive is this one, 2006, with the resolution of 85,900 cities TSP up to optimality. And this is the biggest record today. And in 2013, there is a new record, but this is not the optimal solution. Okay, you can see that this is very close to optimal solution, 0.04% to the optimal solution, but it's not proven. Okay, so today the biggest record is still the one by Applegate and others. And if you look at this evolution of record in number of cities, this is a log scale. You see that it's growing really, really fast in the last years. Okay, let's talk about the vehicle routing problem just a bit more. So Christian talked about this seminal paper of Danzig and Ramseur, and this is where you can find this paper over the internet. Read it, it's very interesting. And of course, today we are far from this original paper. And this is an extract from the presentation from Kenneth Sorensen, who gave a keynote talk at the French OR conference. This is available on the website. You can follow his talk. And he talked about solving the very large-scale CVRP. And this is the type of solutions. So this is computational time in minutes on the left, and instance size. And you see that for an instance of size 1,000, the best, one of the best solutions before the work of Kenneth Sorensen was between 600 and 800 minutes to solve this. And today, the resolution time is closer to a few minutes. Okay, and if you look a bit deeper, so this is the very large size instances, up to 30,000 customers, and the best value they can obtain is given here, and they need 150 minutes to solve the problem using meta-heuristics. Okay, so this is the kind of solution they have today. So they are able to really solve efficiently huge size problems. So of course, we always concentrate on different flavor of VRP, and I just mentioned a few of them. So the CVRP, of course, the multi-depot VRP, where you can start and end a different depot. The periodic VRP, each customer should be visited a certain number of times over a period. The split delivery, which should not be mixed by the split technique from Christian Prince. This is when the order can be delivered by different trucks. Okay, so you have to decide how much quantity you deliver every time you visit a customer. You have VRP with backhauls, so after deliveries, the truck will collect some goods to ship back to the depot. This is very useful for reverse logistic problems. And of course, you have a VRP with pickup and delivery, VRP with satellite facilities, and open VRP when the vehicle do not have to return to the depot. Okay, many people don't understand really why the problem should be open and you don't have to return to the depot. In fact, it's not that the vehicle is not coming back to the depot, it's that you do not take into account the cost of going back to the depot. If you hire a separate company, for example, for transporting goods, the vehicle from this company comes to your depot, and you start paying as soon as you put some goods into this truck. And of course, as soon as the last delivery has been made, you do not pay the cost for this delivery anymore. And of course, for all these VRP flavors, you can add time windows, which makes the problem much more complicated in some times. And okay, just add the TW at the end of the acronym, and then you've got the more complicated problem. I'm going to present one of the problems we solved, which was the transportation of handicapped people. So this problem is a bit different than transporting goods. One of the first origin of this problem is the collaboration with CARPAP. CARPAP is a center, a medical unit for people after a very big car accident. So this is polytraumatology re-education. And in this medical unit, you have full-time patients come for a very long time. Just after the accidents, they can stay up to 2 or 3 years, okay, in the medical center. So this is the full-time patient. And as soon as they are able to go back to their home, they are sent back to their home. But of course, they have daily treatment. So they come 2 or 3 days a week, or sometimes more, for several months, just for re-education. And of course, you have to organize the transportation of these people. So the medical unit should organize the daily transportation of more than 75 patients. And of course, you have to bring them from home to the medical unit in the morning and bring them back in the afternoon. And I've met some of these patients. They spend a lot of time waiting because, of course, the transportation is not organized according to their schedule. It's organized according to the schedule of the medical unit. So they bring the patient in the morning, for example, between 8 and 9, even if the patient has a treatment only in the afternoon. So the guy is there waiting the whole morning, and then he has to wait for the transportation back to his place in the evening. So you can probably do a bit better. And this is our goal. Of course, in the transportation of a handicapped person, then the human factor is very important. You have this type of minivan. You can put 2 or 3 wheelchairs. You can put 4 wheelchairs. You can put 2 wheelchairs plus 2 patients that can walk by themselves. And sometimes you cannot put 2 types of patients together. For example, you have the patient suffering from schizophrenia, and they cannot be, 2 of them cannot be together in the same minivan, because otherwise they hit each other, and they, okay, so it creates conflict. Of course, some of the people, they need oxygen, or so you need some to take care of each patient individually. And they have time and medical constraint. Of course, if you organize a tour for picking up the patient to their place, you cannot have like collecting the first patient at his place and then having a tour of 1 hour long, because the guy will stay 1 hour in the truck, and it's not acceptable for a medical reason. The cost of transportation for the medical unit is calculated from many factors: transportation duration, distance, number of vehicles used, the type of vehicles. As mentioned, you have some vehicles where you can put 1 wheelchair and 2 or 3 patients more, and you can also have vehicles where you can put only 2 wheelchairs, and so on. So you have very different type of vehicle, and the capacity is very different. And one of the problems is that the transportation is mostly done by taxi, and we'll come back on this issue a bit later. So the objective we have in solving this problem is to design a vehicle tour to ensure the daily transportation of the patients while minimizing the total transportation cost. So we have the vehicle capacity as constraints, and as I mentioned, then the vehicle capacity is up to maximum 6 patients per vehicle. So this is a very low capacity, and the demand is always 1, because it's always 1 patient you pick at its place. Okay, so there is no like 2 or 3 patients at the same stop. No, this is always 1 patient at his own place. And the route structure is, the cost is mainly open type VRP problem, okay? So the solution approach we implement here was first, of course, because of my background, I developed an ILP model, which can solve optimally the instances to 55 patients. But of course that was not enough, and that was not quick enough. The CPU time was more than 1 hour for solving these big instances, and because we want to make some simulation also, then we need to implement some meta-heuristics. So we try to solve the Open VRP 1, which is when the demand is always 1, and we compare to the best Open VRP solver at the time, which was the hybrid 1+1 ES from Reynolds and Schneider, and the Taboo Search heuristic ABHT from Derricks and Reiter. And the result we have come from the 110 instances coming from the branchandcut.org website, the Christophides instances, and the Fisher and Jaikumar instances. And the implementation we have made was solving 104 over the 110 instances to obtain the best results compared to the performance of the other solver. And the gap was very low from the lower bound obtained by the relaxation of the ILP model. So that was very encouraging. But of course the problem of the medical center is much more complicated than this. CARPAP is working with the regional public hospital, which is the photo here. Of course, with 2 private hospital units where they have the RMI equipment. Also, they have some specific equipment in these different private hospitals. and 2 different radiography centers. And some of the patients, they have treatment in this unit. So you need to organize also the transportation of this patient to this unit. So it's not only one in one unit. It can be in more than one. It can be in one or more than one unit in CarePap. So the closest academic problem that we would like to solve is the multi-depot open VRP problem. And this is what we have done. So we did not choose the strategy the 2 strategy presented by Christian was the cluster first, route second, or the route first, cluster second. In that case here, we did not choose this strategy, none of these 2 strategies. We just built the routes starting from Clark and Wright and Savings, as usual, and then we use different type of neighborhoods. And so this is mostly the strategy which is used in commercial routing software. Multiple neighborhood search. Okay, so you have a list of neighborhoods and you activate this neighborhood, or you use this neighborhood in random order or sequential order or other. So this is the strategy we have. So we have, of course, some neighborhood intra or inter-route, and we have combined this with ejection chains because this is one of the most powerful technique we have. And we have also a solution improved by taboo search. So in addition to this multiple neighborhood search, we have implemented a specific taboo search to go further. And the neighborhoods that we have are used in token ring. So it means that we use circularly the same neighborhood. So 1, 2, 3, and then 1, 2, 3, and 1, 2, 3 again. Okay, and of course, as in every meta-heuristic, you should balance between intensification and diversification. So try to explore as much as possible the search space, that is diversification. And once you find a very interesting, attractive basin, use intensification to find the most promising solution in that attractive basin. So when we start developing this multiple neighborhood search, we would like to make a specific effort on the presentation of the different neighborhoods. So instead of using the classical neighborhoods, we try to find a common way of presenting the neighborhoods. So this has the idea of having only one specific function that is able to make, let's say, a generalization of all neighborhood, classical neighborhood. So this is based on what we call path move, and we also use the invisible path moves, and we use inter-route exploration. So I'm going to show a bit of this path move. So a path first, so it's called PI alpha, is a sequence of constructive customer in the same route. PI alpha start in route at I in route Ri and visit alpha customer. So this is a portion of the route visiting of a route visiting alpha customer. A path move, so this is 3 parameters in that case. So you remove this portion of path and you reinsert after customer J in the same route or not. Okay, and the path can be reverted. Christian yesterday showed that reverting or inversing the order of the visiting customer can have a very positive effect. So you have this omega parameter, which is 1, do not reverse, or 2, reverse it. And the contribution to length can be computed easily. So the idea was to be able to calculate the cost, the new cost of the neighbor very easily. And because of this kind of technique, of course you can generate quite a large number of invisible routes. Okay, it's easy to do that because of capacity or length, but basically you can repair also this. And to repair this, we use ejection chains. So from invisible path move, ejection chains are used as repair operator. Path move are searched with minimal delta plus length and added to the ejection chain until a feasible solution is found. The cycle detection also and avoidance mechanism is used. So the use of ejection chains was really efficient to repair the solution and provide a new good solution as start for more improvement later. So just to show you what kind of move we have here, I did not give you the detail in the pass and pass move, but the relocate in the intra-route move can be done, the two-up as well. Remember, this is Open VRP, and this is why we don't have the return to the depot. And then you have the relocate, the pass exchange or cross exchange, and the two-up star, making feasible solution. And then you have the split route, which gives you feasible solution, and ejection chain. So in that case, for example, here, you have this blue route, which is added to the route above, giving you a non-feasible solution. And then, of course, this non-feasible solution should be repaired. And this is repaired in 2 steps here. So here are the elements of the multiple neighborhood search with taboo search. So in the algorithm, multiple neighborhood search, we have the intra-route neighborhood, inter-route neighborhood, except the ejection chains. And for the taboo search, then we use 3 neighborhoods, so ejection chain from infeasible pass move with last customer, ejection chain with, from infeasible pass moves with length 2 or length 3. And then the taboo status is the list of visited customers. So this is easy to store, easy to calculate, of course. And the initial solution, in our case, here was the best insertion heuristic based on pace move. So we start with empty solution, and then we use the best insertion heuristics. So this is basically the algorithm. So quite simple. You have the multiple neighborhood search, which is here, intra. And then you have the, where is this? Taboo search here, using in a token ring technique. What are the results we found on this problem? So then we came back to the real problem. So the problem is that when we start talking with CarePap Center, so we met first some people in an electronic lab there, and then we met the people responsible of logistics, and then we met the head of the medical unit, and then we understood that the collaboration is going to be stopped for political or financial reason or for unknown reason. And then we discover by talking to people. In France, this is by law, all transportation of patients are at the expense of the social security. So basically, the medical unit does not care about the cost because the cost is paid by somebody else. So, okay, I'm just clever enough. I say, I'm going to talk with social security. And okay, I was dreaming. I start calling the social security center. And then they give me one number, and then you should call Miss Marple, and then you should call Miss Martin, or you should call Mr. Doctor something, and then, okay. And then after 2 or 3 weeks of trying to reach somebody, then I understood that it was not possible. And the reason is that there is a lobby behind us, and the transportation of patients is done by the taxi drivers. And of course, the taxi drivers, they are paid by Social Security, and this is a large part of their income, especially in a small city like Lorient, which is, the area is 60,000 inhabitants, so this is not a big city. And of course, we have, I don't know, in Lorient, 27 taxi drivers. So if you remove the cost of this transportation of patients, you remove part of their salary. So there is a huge pressure from the taxi driver not to change anything. The problem is that everybody knows they cheat the system. For example, in a taxi, they can transport 2 or 3 patients. But when they give the invoice to the Social Security, this is 3 transportation. Every time. Everybody knows that, so it's not a secret. But if you want to start fighting against the taxi, then you are in trouble. So I don't want to be in trouble in Lorient. This is a too small city. Okay. what was the return for us? Because of course we need to have this return. First, we have this very nice implementation of the multiple neighborhood search with taboo search, and this specific structure of the path move, which is very interesting and very easy to use. And also it was our first experience with graphical interface. And we show that if you don't have a graphical interface, it's very difficult to sell your work to the people. What we are able to do is produce some tables with results, and people are really, people from the academic are really easily convinced by the quality of the results, just by looking at the tables compared to the literature or compared to other things. But not the industry. I mean, they want to see something they can understand more or less easily. We would like to test also the performance of the solver we got. And I would like to thank Flavien, he's not here this morning, okay, PhD student. Oh, okay. Flavien. Okay. Okay. You have a good excuse for him, thank you. Okay, he made a very impressive work on the code to be able to solve these large instances. So just to show you, so this is the initial solution and the time in minutes that we have. And this is the final solution, and so this is the gap to the best known solution given by Kenneth Sorensen and others, and the running time. So you see that this is the running time from Kenneth, and this is the running time we have. So more or less we are at 2-3% of the best known solution for the largest instances with a running time which is more or less similar. And in our opinion, this is a good start for working with other VRP variants. We know we are not going to win the race, but this is not the goal of our approach. The goal is to have a safe, stable solver for VRP problem. And of course, if you want to publish in academic journals, then most of the time people want want you to win the race, but this is not our goal. We want to have a good solver for VRP problem, able to be extended to many variants, which is the case here. Easy to implement, easy to understand for us. And this is what we reach here. And compared to the results given by Kenneth Sorensen, we are quite satisfied. Okay. But then if you want to try to solve problem to reality, then you come to the stochastic variant of the problem. Now, stochastic is a very bad word. You should always call this real-life instance or real-life problem. But stochastic is speaking to people, or maybe more. So maybe before talking about stochastic parameter, reality is already much more complicated than what we solve usually. Most of the instances we have in the literature come with the Euclidean distance, so easy to calculate. But in reality, the distance graph is not symmetric. You don't have Euclidean distances, the triangle inequality is not respected, or many other things. So the stochastic parameters are everywhere. First, if you talk to people, you don't talk about distances, you talk about travel time. People in company, carrier company, they care about the number of kilometers, but they care much more about the time. Also, you have customers that may raise new orders, or customers that may cancel their orders, which appear frequently. And also, you have the quantity to be delivered or connect, which is not precisely known. For example, I work, when I was in Valenciennes, I worked with the Citroën industry, building the minivan for Citroën. And at the beginning of the week, they have more or less a good idea of the demand for the week. But the demand will be more precise every day, even every half day. So you have like, we need this type of part, so we need quantity for the week about 100. And then you know at the beginning of the week that 100 will be 80, and then a bit later they say 85. And then the next day they say, okay, it will be 82, and then, okay, so it changes all the time. So the quantity are not precisely known. One of the very nice examples is the stochastic capacitating arc routing problem. Christian presented the COP yesterday. So the COP is the problem of collecting some item on the edges. It's very close to the waste collection problem. But waste collection is much more complicated than the academic COP problem. You have stochastic in a sense that the quantity to be collected is not known in advance. And this is a multiple objective because, for example, if you organize the tour of this driver, the garbage collector driver, you don't want to have one tour of 2 hours and one tour of 16 hours. The guy, they work the same number of hours every day. So you should balance the length of the tour. So we try with Christian and Philippe to solve this multiple objective stochastic corp. So this is the kind of solution we can obtain. So this is the initial population. It was solved with an SGA2 with local search. So you see that this is here total travel distance, and this is the max span. So this is the length of the longest tour. Okay, so this is the initial solution. What is very interesting in the case of this stochastic problem is that for one point you have the point represented the, let's say, average value in each of the two dimensions, and the square around, this is the standard deviation, plus minus the standard deviation in two directions. So here you have a sort of Pareto front made by these 2 points for the initial solution, and when we solve the problem, you see that finally you have only 1 point which is in the Pareto front here. So this is a very important issue for a problem in reality. And I have another example for you, the example of Rotritex. Everybody knows this container, you put your old clothes in this, okay? So this type of company, so in Brittany, the company working with this is called Rotritex. I've met them by chance at a meeting round table. The goal of the company is in France, this type of company is called insertion company. So the goal of the company is not to make profit, it's just to give work to people that are long-term unemployed. And the idea is that these people, most of them, they have not worked for 5 years, so they just survive. You don't really know how. And of course, they are not skilled at all. So this company favor manual labor, and the idea is that you should organize the sorting of the collect, of course, and the sorting of the old clothes for that. And the idea behind is to create some job for unskilled or unemployed people. The problem is that when you have a company like this, they have no data for routing, so they have no money first. Okay, so every time they have some money, then just create a new job. So they don't invest in anything. So they have no data for routing, they have no money for routing, and they have no competent people in terms of science for us. More of that, they have one motto. They don't want to pay anything, so better nothing than paying is what they say at the very beginning. Okay, if we have to pay, okay, the door is here, thank you, bye-bye. At the same time, we just told them, okay, if you do not contribute, we cannot really do anything for you. We need some, in some sense, we need some help. But of course, the first step will be for free. So this is, let's say, our contribution to the social problem in France. So this is how we see it. The thing is that the problem they have is very, very interesting. So they have real distances. The classical algorithm cannot apply. They have many restrictions. They want reliable solutions. And they need a user interface. And this is the second experience with this interface we have. Okay, so why don't they just buy a routing software? I already answered this problem. They have no money, no time, and no competencies. So the problem description is the following. They have a small fleet of heterogeneous vehicles. Only six vehicles in the case of Retritex, with only one driver per vehicle. So the other guys, they have their driving license, but most of them, they are alcoholic, so they cannot drive, or they lose their driving license, or they don't have it. The container, they are spread everywhere in Brittany. So you have every corner of the street, you have a container. So they have, I don't know how many containers they have. For the small area taken care by Retritex, I think they have 250 containers. One of the main problems they have is they have no idea on the container filling. So that's the main problem. They can have some information when the container is full because some people, they call them. So the container is full. So this is the only information they have. But most of the time they just discover the quantity when they reach the container. They have also two intermediate storage space. So they have this beach container that's allowed to unload the vehicle and store some goods there. And then they have a minimum and maximum capacity at the depot. So the closest problem we have is this one. Dynamic, stochastic, periodic VRP with intermediate facilities. Complicated to solve. And moreover, they have capacity at the intermediate facility. This is a big container, so you cannot put more than that. And they have this minimum, maximum capacity at the depot. So this is the way they proceed today. They have a seasonal planning made by the secretary. Nice. Clever. Actually, I have to tell that I've never seen somebody which is not a scientific person making a very clever reasoning. So the girl, she noticed that they have two types of routes that need to be created because there is seasonal information coming into the game. Of course, they have no prediction on container fillings. They follow the route, whatever happens. Because the drivers are not very skilled, they have this map, and if the container, if the truck is full, they come back to the depot, and then they unload, and then they go back. Well, this is what they do today. And if they finish the route and the truck is still have some space, then they start the route of the next day. Well, this is what they do today. So, of course, this is far to be optimal because this is no adaptation at all. And there's no way of estimating the cost except after reading the odometers. So they come to the truck and they say, oh, this last 6 months you have driven this amount of kilometers. And this is the only way they have to measure the cost of the route. So of course we need to do something for them. So this is the stock at the depot, just to show you some pictures. So if you type Retritex under Google, then you will find this picture. So this is the stock of clothes to be sorted. And this stock is only for 3 days. So if you don't have a collection for 3 days, then the stock will be empty. So it goes very fast. So you need to have this stock filled all the time and continuously. Otherwise, the other worker, they will not be able to work. And this is the final product. So this is here the clothes that they cannot recycle. So just the material will be sent to Pakistan and reused for something else. And these are clothes that are sorted correctly, and this will be sent to a market in Africa. So there is a second market for every clothes you put there. If it's in a good shape, then they will be sent to a market in Africa. And some of the best here, this is the scarf from different football team or stuff like this. But the best clothes, they have some shops where you can buy for a very low price the best clothes that they keep in France. So this is very interesting problem. A problem is that the project once again has been stopped because lack of fundings. As the very beginning, they say we are not going to contribute, and we were able to provide 6 months postdoc project, but not more. And then it's complicated to to continue without any funding. The thing is that we have a good basis, good algorithm basis, so the same one we have used. The nice interface, so we have a small interface, but this need to be to evolve. Of course, we need real distance calculation, which is complicated. They want real map, Google-like. Okay, they want to be able to understand what they can see on the maps, and they want to have some functionality like clickable, zoomable, visible routes, and so on. And this is far from our competencies, but at least we know that we need this type of interface. Last example before showing you some interfaces. This is the context of the PhD program we start this year with Flavian. This is the Urban VRP problem. So the context is the following. Car and truck mobility are more and more restricted. This is the case in France, but this is the case in almost every European city. So in France they have invented the new critère tags. So this is something you have to put on your windscreen if you want to reach to go to Paris. If you don't have this tag, you cannot enter in Paris, or you can be fined. So depending on the quality of your car and pollution emission, then you will get this one. So this is for electrical vehicles, then this is for other vehicle. Okay. Even if you have a recent vehicle, depending on the size of the motor, and you can have a very low quality tag, and for some places, like if there is a peak of pollution in Paris, then you cannot access Paris if your tag is less than 2 or something, more than 2 or something like this. There is also a plan for toll for city center access, and this is the case for London. This will be probably the case for Paris in a very short time, and this will be the case for many places. You have pedestrian zones which are shared by vehicles, so of course you cannot send a big truck in this zone. You have more and more electric vehicles, including microvans. So these microvans can deliver in pedestrian area because they are electric, so they can have access to this city center. On the last point is the increasing cost for parking. And every city, so it was recent in France, so they changed the tarification system for every city. So each city now is able to choose the cost of parking, and of course it changed the usage of the vehicle in city centers. But even if we have all these problems, we need to reach the city center to deliver goods for logistics reason. Okay. Another factor is this connected mobility. So you have more and more systems where you have information, external information about traffic, or internal information about traffic. You are in a car. For example, some of you probably use Waze for GPS information. And Waze has an artificial intelligence systems giving you the best routes depending on the traffic. Of course, you need to have something smart, because if there is a traffic jam in front of you, you cannot send everybody to the second route, because the traffic jam will be on the second route. So you need to be really clever with what you do. You can have also information on traffic lights in advance. You can have information of parking lots available and so on. So this is going to probably increase a lot. I just changed my car recently, and I didn't have time to list all the new equipment I have in my car. There are much too information coming from me. The good thing is that I have a son of 18 years old, so he's going to read everything. He has already played with all the stuff on the tactical screen. I don't know what, but okay, good that I have a son keen on that. So what is the goal of the PhD program? We want to improve the urban transportation problem, being able to answer tomorrow's challenge, so the one with mobility connected, for example. We also plan to use massive open data, which are now available, which is not really the truth. I mean, many cities, they say that we have open data system, but when you start saying we want to use this data, then they are reluctant to give you access to this. And we want to combine operational research and machine learning. So we are going to face a large amount of data. We need to handle this data and, of course, solve the optimization problem behind. So this is one of the goals of this PhD program. So to start with, we have let's say, reduced the problem size. So we are going to minimize the global cost of the routes. And the cost is not clearly defined. It can be travel time, it can be pollution emission, it can be multiple objective problem. We still do not know. And we have several types of vehicles. So we take here two completely opposite type of vehicles, a bicycle and a minivan. And we have different speed, different capacity, and of course we will have restricted access zone. We are going also to take information from real data. So, for example, we are going to collect data, and I have a small example. If it works, not this one, with vtraffic.com, which is available for free, and this is the real-life traffic in Paris today, now. So this is very clever information because you can see in reds the congestion. So if you have this information in real time, you can probably more easily plan your trips. And with the system here, it's very clever because if you zoom in, then you have real-time information on traffic information. So this is a clever system. Okay, maybe to zoom. Okay. It's not too bad today in Paris. So we are going to collect data from different sources. And if you look at the literature about that, there are very few studies, not much today. So you have people from where, I don't remember where. So they work on spatial temporal clustering. So they try to create, let's say, information. This arc has this type of conjunction between 9 and 12, for example. This is what they say. And you have also a different type of approach based on machine learning, but this is more recent. And this is what we need to work more. So this is not my specialty. This is not a specialty of the PhD student Flavien Lucas, but this is one of the specialty of the other co-advisors. So this is more in machine learning, and we plan to use random forest technique, which is one of the most classical one for making efficient classification and problems. And of course, the idea is to react depending on traffic congestion. So you need to collect data in real time because you want to react in real time. You need to compare with prediction. This is what we want to do. So detect increasing traffic in used roads, or detect decreasing traffic in not used roads, and adapt dynamically the routes. So you can have quick modification. You just change the trip of one car. This is what we call the short repair. Or you can have a long repair, which involve re-optimization in a sense. Okay. And what we plan also to do is that every time something happens, we store the experience as a new data to be exploited later. So we are going to make this database of information more dynamic in a sense that every new experience will be stored and used as a case base for later. But we have a lot to learn still on this problem. So just a very small example, if you have one depot, 5 vehicles, and if we say that you can visit only 8 customers per vehicle. So if you solve the classical CVRP solution, then you have this one, the Euclidean distance. But if you take into account the city center, dense area, or sparse area, of course you are going to use 2 types of vehicles because some of the city center cannot be accessed by classical vehicle. So the CVRP solution is this one. But if the city center is not accessible to the big trucks, then you have to use the different type of vehicle for the city center. And for example, you have already drive to the dash line, and the full line is the remaining trip. And this red area is one area where you have less congestion than previously planned. So basically what you can do is you can change the route dynamically of the track. So you need to have some efficient solution procedure to be able to adapt in real time. So this is one of the reasons we do not need to have the optimal solution of the problem. As mentioned by Christian, we need to have efficient operator to repair the solution in real time and provide good solution dynamically. Okay, so how we are going to combine machine learning and OR? This is the unknown part of the thesis for the moment, so we still expect a lot from this. Of course, we are going to learn, so the instance generation, for example, is one of the most important problem. We are going to solve the problem using the basic algorithm we have, and we are going to put in some learning technique to create information, additional information, using the past experience. So then you can create your initial solution, solve, and react and adapt, which is what we expect to do at the end of the thesis. So we still have many open questions. How making the resolution really dynamic? This is very complicated because you need to have real data available in real time. And for example, vTraffic was, before being called vTraffic, it was an open platform. It's not open anymore because they've seen that there is a market for that. So it was open, it's not open anymore. So for example, you can use it as the website I've shown you, but you cannot have API to collect information. Google, for example, you can have for free traffic information, but as you may know, the number of calls to Google API is limited per month. You are allowed to do something like 5,000 calls to the Google API interface per month, and 5,000, every time you need to put a point on the map, this is one call. And you need a distance between 2 points, this is another call. You need, okay, so you see that the limit of 5,000 comes very rapidly. That's why 2 years ago I just black out the university for Google for 2 days, because I used this software calling several times, and then Google detect that my IP was belonging to university. So for 2 days, the university was not able to access Google data because of me. Okay, nobody really knows in my university, so it's not a problem. So we need to have real data exploitation. This is one of the challenges we will face. And also, we do not know at the time which performance level we can have. So the size of the instance, the running time we need, or the reaction time. So these are open questions today. The operational aim of this program is also to be able to handle several types of vehicles. So as mentioned yesterday in the lab session by Christian, the number of vehicle types should not be too high, because then the problem is much more complicated as soon as you have many types of vehicle. We have also some partner for industrial expectation for performance. We are partner with IFSTAR, which is a French Institute for Transportation, and they say that we need to have that type of performance. We need real data, restricted area. We are going to handle this. Okay, so the conclusion is that we need a very efficient interface. And this is what we are going to see now shortly. I don't know, how much time do I have? Enough. Okay. So I will go to the end of my slides. Good. Okay. Interfaces, this is not our job. This is very complicated when you come to define an interface. And I've worked on several routing projects in the past. So this is the list of the projects I have here: school bus routing, inventory routing, robust VRP, CARP, bimodal use, urban transportation, or cluster VRP. And not for all these problems I was keen on writing an interface. Some of them we need. So for example, this is the simplest type of interface we can do. This is very easy. This is a Euclidean instance. So you just have to draw a point in the map, and here this is a cluster VRP, so you just have to make a box around the cluster. So this is not complicated. And this is something you can do with LaTeX output or, I don't know, TXZ or XML or whatsoever. So this is easy to make. But this is not very efficient for people in the industry. This is one of the second example we did. We put a lot of effort. This is a bi-objective inventory routing problem. So this is here one period, the root of one period, and you have a slider here, and you can move this slider, and you can see the different routes constructing over the day. And this is bi-objective, so you have here the two different objectives. And here you have the workload, the stock inventory at the customers. So you see that this is more elaborate, but still not very efficient. And of course, what people need are, let's say, Google-like maps. This is what they know today, so they want to have something like this. And of course, they need to have like a button on the left and stuff like this. But this was not enough. We should capitalize on previous experience. We should find a way to reuse our own work, concentrate on what we know, which is OR in our case, and let the rest. And of course, my idea was to try to disconnect as much as possible the interface to the optimization part. So trying to find a way of having the minimum relationship between the optimization algorithm and the interface. Of course, if you have already developed some interface for any type of problem, as soon as you want to have like dynamic possibility or click and move points dynamically, then you need a very strong connection between the optimization software and the interface. And we do not want that. So what we did instead was to call some specialists from the human-machine interface. That was the idea behind. And we conclude with them that the best way is to use a sort of web service. Why the web service? Because the web service is something that can be used on any type of platform. Okay, you can show something, for example, using a tablet or a mobile phone. It works. It should work. You can make a demonstration at the industrial location without bringing your big PC and big tower. And the calculation can be made on a distant server. So this is the idea behind. And I'm going to make a demo. So we already noticed with Pierre is going to make the lab session, that the demo is not working here. It works when you are connected to the Wi-Fi up in the amphitheater, but not here. So, okay, I'm going to cheat you. You will see. So this is the solver we have. We have made a web service solver. You can just, okay. The link is in the slide, so you can play later on this. So for example, we have here a list of problems that we have already implemented some solver for that. I'm going to start with the simplest, the traveling salesman problem. I'm going to show first what it works and then show you what it does not work. So for example, I can create a Euclidean instance. So Euclidean instance, this is very simple. You have the square here. You can drop points. Okay. Almost everywhere. Then I just load the points. Click on OK. I compute the distance matrix, which is very easy for the Euclidean distance. And then I can run the algorithm. So here I have the initial solution, which is random. Okay, just to show you that we have implemented a grasp with the LS solver behind, which is very efficient. Yes. And this is probably the optimal solution for the problem. Okay. Of course, this is not what we want to do. Well, what we want to do is to use real maps. And this is the bug here. So we can create a real instance. So this is the map of Paris. And then I can click on different locations. I can also enter a list of address. I can also enter a list from a list of points that I've stored previously. So this is completely disconnected if you save nothing on the web server. So for example, you want to make a demo with industrial company, then basically you just come with your list of points, or the company gives you the list of points. They load the list of points just to be able to solve it. But once you have solved, nothing is stored on the server. Okay, so you can load the points here. You can check everything is okay. And if you calculate the distance metric, it does not work. We don't know why. So let's make a try. Oh, it worked. Yes. And then you have the TSP here. So this is... And you see, this is the TSP using the real distance, using the one-way street. So, for example, you have this here. You have this small loop. And you see that it's not Euclidean distance. It's really taking into account the different streets and the way you can reach the point and so on. So it might be strange here. We can also see that there is probably a one-way street close to this, so you need to make a loop to be sure to reach the destination and continue your trip. Okay? So you see that this is very easy to use. The goal, if you want to participate to this project, the goal is to create more problems. So for example, let me load again. Here we have only 3 types of problems, but as soon as we agree on the definition of the problem, there is not much to add to the interface. For the VRP problem, what you need to do is that having a depot, which is more information, a capacity of the truck, if all the truck have the same capacity, and then having a demand at each customer location, which is not much to add in the interface. Of course, if you want to have a multi-depot plus different type of vehicles, then you need to add more information. But the amount of information which is exchanged, which will be exchanged between the interface and your solver is minimum. This is basically the distance matrix, if we need to calculate it completely, or if we can find another way. And then some information on the location, some information on the quantity, some information on the type of vehicle, for example. Okay, so this is an excellent idea. So for working. For example, if you want to have a lab session with your students, this could be very pleasant for the students to write a solver. For example, yesterday Christian write a CVRP solver. We can just tell Christian, the input for your system should be that type, the output should be that type, text file, and then everything will be connected to that interface. So the students, they can immediately see the result with visible routes. As I mentioned before also, we cannot click, drag and drop the routes or the location, because as soon as you do that, then you need recalculation of everything. And we want to minimize this information. Okay? So it's not Google-like, but it's independent from Google. It's based on OpenStreetMap, so this is free. Today we have one limitation, which is the distance metric calculation, because we do that on the web directly. But there are many ways of storing the information. For example, once a week, doing the calculation directly on the server, pre-calculation of several distance on the server, and this is very efficient. So this is one collaboration we have with a society in Bordeaux called Mapotempo, and they already do that. So we know how to make it efficiently. So the demo worked. Great. So, of course, you can contact us if you want to participate. And for the people who will attend the lab sessions with Captain Pierre Baumel. Then Captain Pierre Baumel is in the corner there. He's the one behind this interface, so he deserves all the credit for this presentation. Thank you very much.
Thank you, Marc. Do you have any question? Yeah.
Yeah, the question is about the dynamic about the urban logistic. As it's VRP, how could you use dynamic? Because at the moment every vehicle leaves the depot. They need to deliver the customers that already be sated. So the dynamics will be a small amount of performance, I think, in this kind of stuff.
This is completely true. This is one of the problems we know we are going to face because once you plan a vehicle trip, then you have a certain type of goods inside the vehicle. You cannot deliver goods A to customer B if it's not in its demand. But there are some cases where you can make some exchange. And one of the system we think about is having this cross-platform exchange. So there is a point in the city center or close to the city center when you can deliver part of the goods and then you can also collect these goods with a different type of vehicle. So you can make some cross exchange. This is one of the ideas we know. But we already know that we are going to face this problem. So yes. It's nice to have a
Hello. I have a question more or less on the same subject, dynamic optimization of the VRP. My question is, when you do the dynamic re-optimization, is it, for example, instead of doing the customers I and J, I will do the customers I and K, or the shortest path between IJ, I will change it and I will pass through another way. So more or less, is it a complete graph or a city network?
We can have a quick modification which is based only on the route modification, so you just take a shortcut or a detour for the same route without changing too many things, or you can reassign a customer to a different truck as long as it's compatible, as mentioned before, or you can maybe re-optimize completely from the current situation to the end.
This time is about your machine learning part, because as you said, it's real time. You will have data in real time. Don't need so much to predict the traffic state, I think. So how do you want to use it?
The idea is really to have some information, predictive information on the traffic. And for a big city like Nantes, which I know quite well, we know peak time, for example, in the morning, and peak time at lunchtime, peak time in the evening. We know that we can gain some information from this. For example, if you know that Cours des 50 Étages, which is one of the main axes of the city center in Nantes, is really under congestion in the morning, then you are not going to have any truck going through this place because you know that you are going to face congestion. So the idea is to predict congestion over time. And using this information, you can plan routes differently. We are going to use travel time anyway. So instead of distance, we use travel time. If you have a congestion, then you can calculate. There is already some models about the average speed of the vehicles in the city center. So if you use travel time, then the congestion system with predictive information will give you routes that will avoid the congestions.
Other question? Thank you.